Okay. Hello, can you hear me? My name's Judd, and I am the principal search architect for ZVents. We are a local search engine. I'm also the guy that heads up the Hypertable project. Today I'm going to give a brief overview of Hypertable. So what is Hypertable? Hypertable is a high-performance scalable database modeled after Google's Bigtable. It's open source under the GPL license, and it manages massive sparse tables of information where each cell in the table can have multiple time series revisions. The data in the table is sorted by a single primary key index, and this system is implemented in C++. So what is Hypertable not? It is not a relational database. In particular, we don't support joins or secondary indexes. And the reason we dropped these features is because the emphasis has been primarily on scale. And joining two tables that more or less fit on a single machine is a relatively straightforward operation. But when you have a petabyte table that's spread across hundreds or thousands of machines, and you're trying to join that with some other petabyte table, it becomes a pretty major operation. So in this first go-around, we've dropped support for joins and secondary indexes. We envision adding that at some point, but at a higher level. The other thing it's not is it doesn't support transactions. Okay, so how does it improve over traditional RDBMS technology? First of all, it's scalable. The design emphasis, or the underlying hardware platform for a traditional database is essentially a single machine that works. For Hypertable and Bigtable, the underlying hardware platform is assumed to be a massive cluster of commodity workstations, many of which are broken. And by having that as the hardware upon which the system's designed, that's essentially what makes it scalable. That's why you can't take an old traditional database and just make it scale. The other improvement is Hypertable can achieve an extremely high random key insert rate. You can insert keys in random order at a rate of millions of keys per second, and then you can turn around and scan cells out of that same table at millions of cells per second. Okay, so the data model. Data in Hypertable conceptually is a sparse two-dimensional table where each cell in the table can have multiple cell versions. And each cell in the table is identified by a four-part key. The first part is the row key, and that's just a null-terminated string. The second part is the column family. And the column family is somewhat analogous to a traditional database column. It's represented as a single byte, so there's a limit of 256 columns. And this is something that's defined a priori at table creation time. It's part of the schema. The third part of the key is this column qualifier. And the column qualifier is, it's not something that you define up front. It's considered user data or data that's supplied by the client. And there's no constraints on the qualifier. It's just a null-terminated string. And the fourth part of the key is this timestamp. Okay, so this is my best attempt at a visual representation of a table in Hypertable. I took this from the Bigtable paper, where the running example is their crawler database. Each row in this crawl DB table represents one of the pages that they crawl. And on the left here, you'll see there's two columns. One is title, and that just contains the title of the document. And one is, or the next one is content, and that contains the actual content of the page crawled. And if you notice sort of the stacking effect, that's supposed to represent multiple time series revisions of those cells. Google, in fact, keeps 3 copies of the data that they crawl so that they can do change rate computations, among other things. And then this third column on the right is the anchored column, and it illustrates the use of the qualified or the column qualifiers. A typical search engine doesn't just index the contents of the page. So for example, if you have a page that's just a JPEG image of a Ferrari, it doesn't actually have any text in it. But the way that a search engine surfaces it is it takes all of the anchor text from the remote links that point to that page, and they index that text as part of the page. And this is how it's supported in the crawl database. There's the anchor column. The qualifier is the URL of the remote page that's pointing to this page, and the contents of the cell is the anchor text. So they can just scan a single row and get all of the text to index for this particular page. So now that sort of complex sparse 3D table is actually under the hood represented simply as a flat sorted list of key value pairs. On the right you have the keys, and you can see the 4 parts. There's the row key, which is just the URL of the page, reverse domain name, so that pages in the same domain sort together, followed by the column family, title, content, or anchor, followed by the optional qualifier, which is the remote URL for the anchor column, followed by the timestamp, and then the value is just the contents of the cell. So if you were to pull up the code, you basically see a bunch of data structures that just simply have sorted lists of key value pairs. Okay, so tables and hypertables start out in life as a single range. And as data gets inserted into the range, it'll grow and grow and grow and eventually hit a threshold. By default, it's 200 megs compressed. And once it hits that threshold, the range will split into 2 ranges. And one range will remain on the server that held the original range, and the other range will actually get reassigned to another machine in the cluster. And this process continues on, and that's how a table scales and load gets distributed across the system. So here's another kind of these next few slides illustrate how you can actually go about adding machines into your cluster. So let's say you start with these 2 tables. You have the session table and this crawl database table. And for the sake of argument, say you have 3 servers. Well, the system over time or those tables will split into a bunch of ranges. And so this kind of illustrates that we have these 3 servers here, each holding bits and pieces of the various tables in the system, and they're full to capacity. So to scale, it's simply a matter of just adding 2 new machines, firing up the Hypertable server processes on them, and the system will detect that 2 new servers have been added to the system, so it will automatically migrate ranges from the overloaded machines onto the new machines that have plenty of spare capacity, thus having a balancing effect of load across the entire system. Okay, this is the 10,000-foot overview of the system. This big purple cloud here on the left is what we call hyperspace, and it's our equivalent of Google's Chubby service. It's a highly available lock service and provides a file system for storing small amounts of metadata. Google refers to Chubby as the root of all their distributed data structures, and we use it in the exact same way. Basically, when a server comes up, the first thing it has to do is contact hyperspace, and once it has done that, then it can hook into the rest of the system. And down here, you'll see these range servers and the DFS broker. The range server is the process that's responsible for managing the ranges of table data. And you'll typically in your cluster, you'll see a range server running on every node in the cluster. Now, Hypertable is actually designed to run on top of a distributed file system like the Google file system. But we're not tied to any one particular file system. So we've created this DFS broker layer. And the DFS broker actually speaks this normal file system protocol with the range server on one side, and on the other side it speaks the file system specific protocol. And the distributed file system that we typically run on is the Hadoop distributed file system. So we have a DFS broker for HDFS, and there's another GFS clone out there called KFS. It's actually just been renamed to CloudStore, but we have a broker for that one. And then we also have a local broker that just reads and writes to the local file system, and we use that for testing. And then up on the right, you'll see this thing, the master. The master is responsible for handling metadata operations like table creation, altering tables, dropping tables, things like that. Client data doesn't actually move through the master, so it can be down for short periods of time without anyone noticing. And so we use a hot standby approach for high availability there. Okay, so this is sort of a graphic that describes the range server and how scans happen. First, with the updates. When an update comes into the range server, the first thing it does is it writes the update to a commit log in the distributed file system. And then it updates this in-memory data structure that we call the cell cache. Now, that happens, that just continues to happen, and then over time, as the system runs low on memory, it'll start to compact. And what that is the cell cache, or the in-memory map of key value pairs, gets written out to a disk file or data structure that we call the cell store. And the cell store basically is just a sorted list of compressed blocks of key value pairs. And this continues to happen. Now, when you go to actually query a table, internally there's this thing called the merge scanner. And the merge scanner will basically create an iterator on the cell cache and then open these cell stores and essentially create iterators on each one of those and do a heap merge of all the key value pairs, and that's how scanning happens internally. Okay, this is a client API. Okay, yeah, so this is kind of typical methods that you would see in a database: create table, open table, alter table, get tables. We have this table abstraction, and it's pretty simple. It just has two methods: create mutator and create scanner. A mutator is how you insert data into a table or delete rows and cells in a table, and a scanner is how you scan over ranges of a table, or essentially do queries. The mutator is shown right below. It's got a set where you give it a key spec and a value, or a set delete where you can delete a cell or a row. And then it's got this thing flush. By default, the mutator will actually buffer up a bunch of inserts and deletes. And then once its internal buffers have filled up, it will then flush them out to the range servers. But you can force that flush to happen by explicitly calling this flush. And then down here, we've got the table scanner. It's pretty simple. If you look back up on the create table method, there's this scan spec that is the parameter. That's essentially the predicate for the scan. And the table scanner just has this next call, next. It returns true until it's finished, then it returns false. And this is that scan spec. You can say, I only want one row. You can specify the number of cell versions that you want. You can pick or specify specific columns. You can add row intervals and things like that. Now the principal or the main API is the C++ API, but we've developed something called the thrift broker. And Thrift is a, let's see, it's a community, it's a toolkit developed by the people at Facebook, and it's sort of a Corba-like IDL system where you can generate a server and client bindings in any language. And so we've built this Thrift broker, and this gives us language bindings for all these languages. Okay, optimizations. So remembering back to the cell store, the cell store consists of compressed blocks of key value pairs, and also the commit log. Each commit log write is compressed as well. And we've implemented a bunch of compression schemes, or integrated these compression schemes. We've got zlib, LZO, which has a high decompression speed. QuickLZ, which is a relatively new one that's kind of a nice trade-off between zlib and LZO, and then BMZ, which is a long common substring compressor, and it's really good for data that's highly replicated, like crawl data, where you might have 3 copies of a very similar data. It does a really good job at compression. By default, we just use LZO because empirically that's proven to be the best. There's 2 levels of caching. We have a block cache that the compressed block in the cell store gets cached in memory uncompressed. And then this query cache, which we haven't implemented yet, but intend to at some point. Okay, access groups. Access groups are kind of cool. They're, from the previous presentation, he was describing the differences between a row-oriented database and a column-oriented database. Well, this kind of gives you control to make the database however you want. It basically, it's a performance thing, and it allows you to physically store related columns together. So for example, this create table statement down here, it's defining a table, crawlDB, with 4 columns: title, content, page rank, and click rank. And then it defines these 2 access groups, default and ranking. And what that does is that tells the system to physically store the data for title and content in the default access group, and physically store the data for page rank and click rank in a separate access group. That way, for example, you had a table with 100 columns, but only 2 of those 100 columns are accessed very frequently. What you can do is put those 2 columns in their own access group, and then when you go to scan those 2 columns, you're only having to do I/O for just those 2 columns, not all 100 columns. Okay, so the keys to performance with this system are, first, it's implemented in C++. The system is CPU intensive, and it's also very memory intensive. And the performance of the system is dictated in large part by how much physical RAM is available. And by going with C++, that gives us much better control over memory. And all communication in the system is asynchronous, so that allows us to keep the number of threads down to a minimum, but maximize the amount of work that's done by each thread. And locking is fairly fine-grained. Locks are pushed down about as low as possible. So here's a performance test. It's a little old, but it kind of gives you an idea. AOL inadvertently published some query logs that we got a hold of. Actually, no, that's not. That was a different test. But anyway, we used those to create a simulator to simulate that data. And we got Hypertable running on a 9-node cluster. The average size of the row key was just 9 bytes, and the average value size was just 18 bytes. Replication factor of 3. It was a 9-node cluster. We had 4 simultaneous insert clients, and we achieved a sustained insert rate of over 1 million inserts a second. Now that was buffered. We weren't calling flush after every insert, but nonetheless, that's pretty good. And then scanning, we could scan at approximately 1 million cells per second.
This with Hadoop distributed file system?
Yes, it was running on top of Hadoop. And this was just a small kind of single node test that we ran recently, where the file system was the local file system, so it was just one copy reading and writing from the local disk, and putting 250 megabytes into the table. Each value was 1K. In batched mode, we were doing 31,000 inserts a second, or 31 megabytes a second. And non-batched, we actually saw 500 inserts per second, which is pretty good because it's calling flush after every insert. And then random reads, almost 6,000 queries a second. And yeah, I'm not sure why the batch write performance is worse on the in-memory table, but anyways, the random reads are better there. So. Okay, so a few months back, Baidu actually became oh, you about done here? Okay, let me just finish this slide real quick. They became an official sponsor of the project. They have a team of engineers in China. They're China's leading search engine, and they've deployed it internally on a 120 node cluster. They're pretty fat machines, and they're stuffing about 500 gigs of data into Hypertable per day. I think they're up to 2 or 300 terabytes of data, and they have their own in-house fork of Hypertable as well as Hadoop that they've made a bunch of modifications, but they're feeding ideas back and patches, and so we're getting the benefit of these guys pushing the boundaries there. All right, thank you.